Okay, today we are going to introduce an example to explain how to solve a differential equation using Fourier series. We are going to be interested in the example that is going to be very similar to the harmonic oscillator. We are going to introduce the differential equation m, the second derivative of x with respect to time, plus kx equals f of t. Okay, this is like we're representing, for example, the motion of a spring that has some angular frequency. But in this case, there is, for example, an external force f of t. And the important thing here is that this t is going to be periodic. Okay, so this spring will be oscillating, but there is an external force acting on this spring with magnitude f. And this f changes on time. Okay, so looking at, well, this function needs to be periodic. We are going to introduce an example of a function f of t that will be useful to solve the differential equation through the Fourier series. We are going to establish that this is going to be from negative pi to pi here, and we are going to draw the graph of the function. Here is going to be from 0 to 1, okay? And remember, this needs to be periodic to work out. So let me draw again the line of the function. We will have something like this, okay, where this is the number 2. Here is t equals to 3, okay? And we keep going. So we can easily see that this function f of t, well, it is periodic. And also, well, it is easy to notice that the period is equal to 2. Okay, so the period of the function is equal to 2. Okay, so if we would draw the function on negative values of t, we will see that this keeps going like this. So it is easy to notice that this is an odd function. Okay, so looking that it is an odd function, remember that if you have an integral on a symmetric interval from negative p to p, for example, of an odd function times an odd function, well, this is going to represent an even function. Okay, so yeah, looking that, well, we are integrating an even function. Well, this is going to be twice the integral from 0 to p of that even function. Okay, but if we have, for example, the integral from negative p to p of an odd function with an even function, well, we are going to get that this is going to be an odd function. And looking that it is odd on a symmetric interval, well, this is going to be equal to 0. This is important because when we take this function f of t into the Fourier series formulas, well, we are going to multiply this f of t with the cosine function and the sine function. So that means that looking that cosine is an even function multiplied by an odd function f of t, well, the result is going to be equal to 0. So that means that we are going to take just the case when we need to multiply f of t times the sine function. Okay, so that is going to be the only Euler-Fourier equation that is going to survive in this case, because we are dealing with a function that is odd. Okay, perfect. So that means that to be able to find the Fourier series of f of t, well, we just need to use one of the Euler-Fourier equations. Also, well, it is important to notice that the structure of this function, for example, in the interval 0 to 1, well, it is easy to see that f of t has the form pi t. So it is just a straight line with inclination equal to pi. Okay, perfect. Okay, so if we want to find, for example, the term b sub n that corresponds to the sine term on the Fourier series, Well, we remember that this is equal to 1 over p, the integral from negative p to p of f of t sine of n pi t over p dt. Remember, well, we were working with these formulas on the domain of x, but looking at this example, this differential equation is representing a motion that changes on time. Well, we are working now with the variable t, but it's exactly the same. Okay, so again, looking that this is an odd function and this is an odd function, well, the result is going to be the integral of an even function, and integrating on a symmetric interval, well, this is just going to be twice 1 over p, the integral from 0 to p of f of t sine of n pi t over p dt. Perfect. Okay. So what is the period of the function? Well, we said that it was 2, but looking at p, well, is the half of the period. Well, p in this case is going to be equal to 1. Okay. And we said here that f of t was equal to pi t. Perfect. So that means that we have all the pieces to calculate b sub n. This is going to be equal to 2 over, well, it will be 1 here because p is equal to 1. So it is just 2 times the integral from 0 to 1 of pi t sine of n pi t dt. Okay, perfect. A very easy integral to solve. Let me just call this as u and this as dv to use integration by parts. So this is going to be equal to 2 pi times, well, it will be u, which is t, and let me recall that b in this case, well, it's going to be the integral of the sine of n pi t dt, which is going to be 1 over n pi, actually a minus here, cosine of n pi t. Perfect. So we have here u times b. So here we have a minus and then cosine of n pi t divided by n pi from 0 to 1, and then minus the integral from 0 to 1 of, it will be minus, so this becomes a plus, cosine of n pi t over n pi times du, but that is equal to dt. Okay, perfect. Okay, look here that when we evaluate at 0, this is going to be equal to 0 due to this t that is multiplying. So the only term that is going to survive is when t is equal to 1. So this is going to be, and 2 pi divided by n pi is just going to be 2 divided by n. And here we are going to have minus cosine of n pi. Okay, perfect. So here we are going to have again 2 divided by n by cancelling this pi with this pi and with this pi, and the integral from 0 to 1 of the cosine of n pi t. So that is going to be, well, 1 over n pi, the sine of n pi t from 0 to 1. Okay, but it is easy to notice that, well, if t is equal to 1, we have a multiple of pi. So remember that the sine of a multiple of pi is always equal to 0. And of course, the sine of 0 is equal to 0. So this means that all this is going to be equal to 0. Perfect. So we have that the final result of this integral is minus 2 divided by n cosine of n pi. Okay, and remember that n goes from 0 to infinity in the natural numbers. Okay, so, and remember that this can be seen as minus 2 divided by n times, or let me write this in this way, it will be 2 divided by n of minus 1 to the n plus 1. Look, when we have n equals to 0, we have negative 1 to the 1 power, so that is negative 1. So we get minus 2 divided by n. So that is correct. So when n is equal to 1, we have negative 1 squared, that is a negative 1 positive. So the result is just 2 divided by n. Perfect. So that means that we are correct. This goes from n equal to 0 to infinity. Perfect. So this will be the value of b sub n. Okay? Perfect. So if we remember the Euler-Fourier equation for a function f of t, we know that this can be seen as f of t equals to the sum from n equals 0 to infinity of b sub n times the sine of n pi t divided by p, but remember p is equal to 1. Okay, so that means that we can define our f of t as the sum from n equals 0 to infinity of 2 over n minus 1 to the n plus 1 sine of n pi t. Okay, and looking at, well, the sine of 0 is 0. Okay, we can start this sum from 1. Okay, perfect. Okay, so we have now just found f in terms of a Fourier series, but right now we are going to be interested in finding a particular solution for this differential equation x sub p of t, okay, that will satisfy this differential equation. Okay, so right now what we are going to do is to propose a particular solution of the differential equation that we have the form x sub p of t, the sum from n equals 1 to infinity of a b sub n, and looking at, well, notice that this b sub n is different from the other b sub n that we calculated for f, and this will multiply sine of n pi t. Okay, so the differential equation that we are working is a second order differential equation, so that means that we need to find the second derivative of this. So the first derivative is going to be the sum from n equals 1 to infinity of b sub n, which it doesn't depend on t, so that means it is a constant. And we take out n pi and multiply it by cosine of n pi t. And then x sub p double prime of t is going to be equal to the sum from n equals 1 to infinity of negative b sub n squared pi squared sine of n pi t. Okay, perfect. Okay, so if we substitute this on the differential equation that we have, we are going to get that this is going to be minus m, the sum from n equals 1 to infinity of n squared pi squared sine of n pi t, and, well, I forgot a b sub n here, then plus k times x, which is going to be the sum from n equals 1 to infinity b sub n sine of n pi t, and this is going to be equal to the f of t that we found, which is the sum from n equals 1 to infinity of 2 divided by n minus 1 to the n plus 1 sine of n pi t. Perfect. So looking that we have sums that start on the same index, n equals 1, and we have a constant factor sine of n pi t, we can equal the coefficients of each term of the sums in this equation. So we are going to get that minus m n squared pi squared b sub n plus k b sub n is equal to 2 divided by n minus 1 to the n plus 1, and that's it. So if we take this common factor b sub n for this, we are going to get that b sub n is equal to 2 divided by n minus 1 to the n plus 1 divided by minus m n squared pi squared plus k. Okay, perfect. Let me see if we can do anything else. It seems like not. So with this we can already calculate x sub p of t. remember that we defined it as the sum from n equals 1 to infinity of this b sub n. Let me write it in this way: 2 times minus 1 to the n plus 1 divided by n times k minus m n squared pi squared, and then times sine of n pi t. Remember that the proposal that we made for x was this sum over here that includes this sine of n pi t. Perfect. So this will be a particular solution of, for example, remember maybe a spring that is oscillating. Okay, it has a constant k, and this block has a mass m, and in this case there is a particular force with magnitude f of t that changes on time with periodicity equal to t. Okay, perfect. So the solution of the differential equation that describes this motion, well, it's given by this Fourier series of x. Okay, this is a particular solution of this problem, and a very intuitive way to explain how to solve differential equations through the Fourier series and Fourier analysis. Okay, an important fact of this is that, well, look that we have that the Fourier series is depending on the sine of n pi t divided by p. It is going to be very interesting that if it results that there exists an n, which is of course a natural number, maybe an integer, but let's just think here right now on natural numbers, where the quantity n pi divided by p is equal to omega, where omega is of course the square root of k over m. Okay, it results that if there is an n that satisfies this equation, well, we can say that at that n we have pure resonance. Okay, in this case where there exists resonance. Perfect. So this will be the final conclusion of the video.